like to introduce now their real names, Tyler, David, and Zach, to discuss their research this semester.
Thank you, Dr. Kowalski. Thank you all for coming this afternoon for our presentation on the wireless motion tracking system. My name is Tyler Fitzsimmons.
I'm David Bruce.
I'm Zach Glazer, and our advisor was Dr. Kowalski. So here's our presentation overview. We're going to start with going into the objective statement, then next the background of wireless motion tracking systems, and we'll explain exactly why they're necessary and what's currently on the market. Next, I'm going to discuss the overall goals of the project. David's going to start out with the electrical section of the system breakdown, and Zach, the mechanical section. We're going to go back to David, and he's going to conclude with the results, conclusion, and the future work. The objective statement for the project was to develop and implement a wireless motion tracking system with custom real-time software program for analysis. So why are we even working on a motion tracking system? So there actually is a huge need for such technology. Something that you guys have probably seen actually in the news lately is with the sports application with respect to concussion injuries in the NFL. So motion tracking systems were used to help identify that problem and diagnose the issue. Furthermore, there are military applications, there are virtual reality and computer animation excuse me, applications, which help a lot of the video games everybody plays these days. And finally, we're going to focus on the health, physical therapy, and repetitive strain or stress injury problem, which we see as the biggest benefitter of motion tracking systems. So what is an RSI, or repetitive stress injury? It's a condition where pain and other symptoms occur in an area of the body which has repetitive tasks. And these are primarily in your arms and your hands, but our project focuses primarily on the arms. And unfortunately, it affects a large group of people. Approximately 2 million Americans every single year have RSIs due to ergonomic problems. Probably most of the people in this room that sit at desks for long periods of time. And 1 in 3 computer users already have symptoms of RSIs, especially young people. Now, it's amazing that 50 cents of every single dollar in the United States, it's estimated, is spent on RSI treatment and rehabilitation. So how do you get an RSI? Unfortunately, like I said, it's incredibly easy. It's from sitting at a desk too long. It's from the person in the manufacturing facility that puts the box in the same location day in and day out, or the person at their desk that files the same file every day. So unfortunately, like I said, it's incredibly easy. In addition to the personal cost, there are monetary costs. So a few years ago, OSHA reported that approximately $1.82 billion was spent solely on repetitive stress injury rehabilitation. And the graph on the right side shows you that for worker compensation claims, they're approximately twice as large as any other claim in the United States. So again, it needed to be worked on. And there are people that are trying to develop motion tracking systems. So they can be broken down into 2 main categories that you can currently get: the video tracking and wearables. So video tracking is what you see on the right side in the picture. And that's where a person has dots around their body, and they stand in a group of cameras, and the cameras track those dots and output it to a computer. Now, if you imagine in a manufacturing facility, this would be incredibly hard to place cameras around every single person to track them. So it's not very conducive. The second one are the wearables. So wearables, whenever I say that, most people think of the Apple Watch or the Fitbit. But that's not exactly what we're working on. Those are overall body motion trackers, and we are really targeting specific limbs of the body. Now, we are building upon work performed by a previous group, actually last spring, and the members are Jad Lababna and Justin Wolford. And they had 3 main things that they focused on, one of which is wired collection of data. They also had wired communication in 2 dimensions, so just imagine an arm moving up and down, and they used an accelerometer and a gyroscope for that. And finally, they had video and data that was post-processed, so they would take the data from the motion, save it, and then later analyze it, where ours is in real time, as David will talk about. Now, what did we do for the semester? We focused on 4 main things: a wireless, intuitive, comfortable, and cost-efficient device. Now, something that should be noted for the rest of the presentation is that we see this device being used by health professionals at the hospital and in the physical therapy setting, but also by the home user. And by just putting on the device, they don't need supervision of a medical professional. And now David is going to go and do the exact constraints of the project.
So to start the semester off, we wanted to set some constraints for our project. First of all, we wanted to use the same microcontroller that the previous team used. Now the reasoning for this is they had some existing code that we could work off of. And also it is the smallest produced microcontroller in the world currently that met our specifications for the project. It also has wireless capabilities, which is our second constraint. And the reason that we wanted to be able to communicate wirelessly is because when there's wires on the, as Tyler mentioned earlier with the other software, other hardware for tracking motion, it inhibits motion in the arm and doesn't allow for a free range of motion test. So it's important that it's wireless for our purposes. The third constraint was that the device needed to be wearable. And the reasoning for this is if we want to track the motion in an arm, then it needs to be attached to the arm to get that information. The fourth constraint was that we wanted to use a 9-axis sensor as opposed to the 6-axis sensor that the previous team used. The extra 3 axes come from the magnetometer that's added in. And what the magnetometer essentially does is it eliminates a lot of the error that you see in a system that only incorporates the accelerometer and the gyroscope. Our fifth constraint was that we wanted to be able to interact with our data and our device via a graphical user interface, or GUI. And the reasoning for this is it's just a more intuitive and simple way to operate the system. Here you can see the overview of our system, and it's very important to understand this slide to know how the information flows and how things communicate together. So in the upper left corner, you can see the 2 yellow shapes representing the sensors on the patient's arm. This information from these sensors would be wirelessly communicated to the receiver, which would then send the information out through the USB cable to the computer, where MATLAB would pick it up and analyze the data that it was receiving. So here you can see our subsystem breakdown, and we broke it down into 3 different subsystems: the software, the hardware, and the clothing apparatus design. For our project this semester, we focused only on the software and the hardware. As you can see, they are color-coded as well. And in the future slide, you'll see in the upper right corner the color referring to the specific subsystem about which we are talking in that slide. So for the software, we break it down into the transmitter, the receiver, and the computer. The transmitter will read the motion data from the sensors, store that data in the microcontroller of the transmitter, then take it and send it wirelessly to the receiver, where it would then store, the receiver would then store that information in its microcontroller, and then send the information out through the USB to the computer, where MATLAB would pick it up and analyze the data that it was receiving. Once again, the hardware for the transmitter is the microcontroller, the motion sensor itself, and the custom designed printed circuit board, or PCB, that we did make specifically for our 9-axis sensor. The receiver has its own microcontroller, and then the computer is its own hardware. Now I'm going to hand it off to Zach to talk about his portion of the system breakdown.
So in our system, we had 2 9-axis sensors. Each of these sensors have a gyroscope, an accelerometer, and an ionometer. So what are these? The gyroscope, it senses a change in rotation and a change in orientation. So think of this as you have your hand straight out in front of you, with a sensor placed on the top of the forearm, and then rotating it. We can pick up that rotation. And if you were to move your arm to a different location, you can also pick up that orientation. So for our accelerometer, that responds to a linear acceleration. So think of this as if you were sitting straight and you were to push a box straight forward. That change in linear acceleration we can pick up. And the magnetometer, that is just measuring a direction towards relative north, magnetic north. So think of this as your Boy Scout compass, but in 3 dimensions. So why do we pick all 3 of these together? Well, we're able to determine our angular velocity, our linear acceleration, and our position. The reason why I added the magnetometer was we were able to determine the direction that you're moving, so you know where the actual arm is going. So this is our sensor layout. We had 2 sensors, again, consisting of the gyro, the accelerometer, and the magnetometer. These were placed at the yellow shapes on the bicep and the forearm. They were placed at the center of mass of each of those locations. determine the center of mass is through anthropomorphic data. And that data is just average lengths of the body, average weights of the body, and we use that to calculate center mass. We used a linkage model, which is illustrated in red on the arm. That was used to determine the forces exerted on the elbow and the shoulder. The reason why we used a linkage model was to take something that's very complex, break it down to its individual components, and then analyze it. So can I have everybody stand up for a little bit? So these 5 motions are typical motions that a physical therapist might make you run through to determine where your RSI is located. So our motion 1 is having your arm straight out and then bending it forward like this. Motion 2, having your arm straight down your side and then raising it to your head. Motion 3 is having your arm back behind your back a little bit and then raising it to your head again. Motion 4 is having your arm straight out, bending your arm in, and then rotating. The last motion is motion 5, which is straight out again, and then across your body. All right, you guys can sit down again. That's your workout for the evening. Later on, David will talk about our GUI, our graphical user interface. And that graphical user interface, you can actually select motions 1 through 5, and it will reiterate how we did this. So this is our printed circuit board, or our PCB. We did design this and fabricate this here at USI. It was designed to have breakout pins from the 9-axis sensor, which is located in the gray rectangle on the picture. This PCB was attached to our wireless transmitter. So this is our finished PCB, our printed circuit board. We have 2 teal wires coming in that are providing power to our 9-axis sensor, which is located in the center, the black rectangle. The other 2 wires are 2-wire communication that is just picking up the data the sensor is providing and then giving it to our microcontroller for analysis. So this is our setup right now for testing. We have our microcontroller and our 2 9-axis sensors. Those 2 sensors are wired directly to our microcontroller so that we can make sure our data we're collecting is correct. And I'm going to hand it off to David. He's going to talk about our GUI and our results.
So here you can see our GUI that we designed to operate our system. We have it divided up into a few different sections. The first section is the instructions, and those are the green boxes. The upper left green box just is the steps to take you through how to operate our wireless motion tracking system using this GUI. And the lower right-hand box is once you have selected the motion, it tells you the optimum range of motion and the directions of how to do that motion exercise. The next is the user inputs, and those are the red boxes. The upper left red box is the general user input, and as Tyler had mentioned before, when the patient takes this home, that'll be for their use, because then all they have to put is the weight, the height, and whether they're male or female. Then they'll be able to operate the system. The box directly below that is the advanced user inputs. That's intended to be used by the medical professional who can take more specific measurements and then use that to operate the system. Finally, the last red box over above the motion is the drop-down menu where you select from motions 1 through 5, depending on which motion you want to do. The next section is the yellow box in the upper left-hand corner. These are the system controls. The start is the button that starts acquiring the data for your system, and the stop would stop that operation, and help is for if you get stuck. The next section is the video walkthrough, and that's the purple box on the right side. You can see Zach here. Just as he showed you here a minute ago, this will be a video of the motion that you specifically selected and showing you visually how to do that motion. So the final section are the orange boxes at the bottom, and these are the graphs. It's the graphical representation of the sensor information that we are pulling into the system. So this semester we had 7 goals that we set out to accomplish. The first, starting out small, we just wanted to get a reading from a single sensor. So to do this, we programmed our microcontroller using Crossworks to read from the sensor and then display that information within Crossworks. we were able to see that we were pulling information off of the sensor doing that. The next step for goal number 2 was to then take that information and send it out through the USB to be picked up in MATLAB. We then looked at what we were receiving into MATLAB, compared it to what we saw in Crossworks, and we were able to verify that that data matched up, so we were getting successful communication. The third goal was to then take that information and plot it in real time in MATLAB. And we have a video to show that we were able to successfully do that. Here you can see a graph in the X, Y, and Z directions of our accelerometer for this sensor. And you can see as I'm moving it around, it does respond in real time to my motion, and it is portraying that change in motion. And then when I stop, you can see that it flatlines again. So we were able to accomplish those first 3 steps, so we can put a green check mark for those. The fourth goal was to then establish wireless communication. Now to start out, we just wanted to verify that we could do a wireless communication, so we used dummy data, unusable data. We programmed that into the transmitter, and we picked it up with the receiver, and we displayed that information that we were picking up in Crossworks once again. And we were able to see that we were getting the correct data. So for the 5th step, we wanted to attach the sensor directly to the transmitter to pull data from that and send it to the receiver. This is where we ran into problems. We were not picking up anything at all at the receiver end. So we determined that the problem was between the 2-wire interface communication between the sensor and the transmitter. We have contacted the manufacturer of the transmitter, but we have yet to reach a solution, a viable solution to fix the problem that we were running into. So we still wanted to be able to present a system that tracks motion using multiple sensors. So we decided we would wire 2 sensors directly to the receiver, take that information, send it to MATLAB, and then analyze it and plot it in real time. And here again, we have another video showing that we were able to accomplish that. On the monitor above, you can see the X, Y, and Z axes again of each accelerometer for both sensors being displayed. And as Zach moves it back and forth, you can see they are updating in relatively real time. In this particular graph, it is a little bit slow because there are multiple graphs being plotted, so it's a lack of processing power of the computer is the reason that there is a lag in the plot. And here, once again, we're going to zoom in on the accelerometer graphs up on the upper monitor. And you can see that, again, it is responding to his change in motion. And then we also are going to show here the gyroscope and the magnetometer for each sensor. And again, they are also showing changes based off of motion. So again, we were able to put green check marks on goal 4 and 5, or 4 and 6 rather. And to finish off for our 7th goal, we wanted to take all that information and to have it operate through our GUI and display the information in the GUI as well. And we have a picture here to show that we were able to do that. As you can see, the graphs are being plotted. And also we have a video here to show the actual motion tracking, so you can see the motion of the arm and the graph behind Zach there on the computer. And this is all happening in real time. And in the lower right corner, you can see the forces they're acting on as Zach moves his arm. They're acting on his arm. And you can see there is a little bit of error in play here, but that is something that will be worked out in future work. For our purposes, we were able to get motion tracking. So what did we accomplish this semester? We made a custom graphical user interface to operate our system. We made a custom printed circuit board for our 9-axis sensor. We were able to take motion data from 2 sensors and correctly interpret it. And we were able to do a real-time motion tracking and analysis based on that information, as well as a force analysis. And we were able to flush out some commercialization possibilities by doing patent searches and competitor analysis. For future work, those issues that we were running into with the transmitter and communicating with the sensor, those need to be flushed out, as well as some calibration techniques and some error removal for the system. There needs to be a design of a 3D printed housing for the sensor and the transmitter, and as well as this will eventually be a overall full body motion tracking suit, where we just focused on the arm for this semester. So to conclude, we'd like to thank Dr. Klobowski and Dr. Davis for their assistance this semester. We'd also like to thank Dr. Mitchell and Donna Moore, and ST Microelectronics for their hardware donations, as well as Rowley for their donation of a Crossworks license for us this semester, and as well as our friends and family for all of their support. Thank you.
All righty, questions? Nice job. Does your wireless protocol use a standard or is it proprietary?
It's standard 2.4 gigahertz signal transmission.
I'm referring to the protocol, not the frequency.
The protocol is standard. It's so it uses 115,200 baud rate, and the transmission is standard transmission of data for the microcontroller and the receiver.
There are a number of protocols that the microcontroller can actually accommodate, so
Okay,
not
thank
one
you.
specific.
Really good work. I had seen the previous presentation before, and I'd asked a question. I saw that you did the last video where the unit was lifted on the arm. Is there a possible strategy to reduce the noise in that signal, the variation? What I had wanted to do was add this to my robots in the AEC to track three-dimensional motion, and I just wanted to know if there was a way to filter out that.
Absolutely. Right now, we are averaging the data over each signal transmission. So every transmission we get 6 readings, and we are averaging over those 6 readings right now. But in the future work, to help reduce the error, we were looking at additional filtering or averaging to help reduce that. But it is right now averaged a little bit.
So gentlemen, what's your advice to the follow-on team for this project, based on your experience?
A lot of it is kind of reduction in error. Moving forward, a lot of the groundwork is laid, and figuring out the problem with the wireless as the big communication. So in the final video, you saw that the sensor was primarily on the forearm. We had originally had the sensors on the forearm and the bicep that were both wired to the microcontroller, but we actually had high impedance on the wires, and we were not able to get proper readings from the sensor that was on the bicep. So wireless communication is really imperative for the next step in getting 2 sensors communicating in real time accurately.
And so about how long would you expect your application to last for a patient that's using it?
We did compute power usage, and we computed 2 different scenarios, one of which is under ideal conditions, and that was 11.33 hours for continuous transmission of data. The other one is the typical efficiency used in electronics, which is a 70% efficiency, and for that we had 9.33 hours of continual data transmission, which will last the entire workday if somebody were to track usage for a worker.
Any other questions? All right, let's give them a hand.